Hello, everyone. I hope you have enjoyed the last session by Alex, intro into the math for version B of Summa protocol. Just a quick reminder, if you guys have any feedback or comments on Binance issue that Enrico has posted, please share your notes today. As he will be contacting them. And yeah, welcome to the next session. I guess today Alex is presenting the implementation of the main circuit for version B. Alex, stage is yours.
Hi everyone, my name is Alex, and yes, today I will present the circuit of the univariate grand sum approach of Summa that for brevity we call Summa v2. So let's start by briefly recapping what we have learned about Summa v2 in the previous session. So we have a polynomial as our main data structure. That polynomial encodes the user balances, and the grand total of all user balances is encoded in the constant coefficient of the polynomial thanks to all the math that we did in the previous session. So we can obtain the grand total of all the liabilities just by multiplying the constant coefficient of the polynomial by the number of users. We use that data structure in junction with the KZG commitment scheme, which is a natural choice for a polynomial. And to prove the grand sum of the liabilities, we're opening the commitment at the constant coefficient at the point of x equals 0. And to prove the inclusion of the individual users into the grand total, we provide the opening proofs to the users corresponding to their points in like on x-axis, corresponding to the omega raised to the power of the user index. So what does it mean for the prover? What should the prover do to accomplish all these steps? First of all, the prover needs to interpolate the balances to produce the balanced polynomial. Then the prover needs to produce the KZG commitment to the polynomial. And then the prover needs to publish the opening proof at x equals 0 and also individually provide the KZG opening proofs proving the individual user inclusion. So on the verifier side, what the verifier should do to enable the protocol is first to observe the commitment that the prover has produced because this is public. And then after receiving the proof of the grand total sum and the individual proof of inclusion, the verifier needs to verify the corresponding proofs and also make sure that since both proofs are verified against the same commitment, then the verifier can conclude that their balance was indeed included into the grand total. So all this time we have been talking about polynomial interpolation and the KZG commitment, and maybe a natural question in your heads would be, do we even need a ZK snark here? Like, why would we need it if we're just talking about the KZG commitment? But the answer is yes, we still need the ZK snark for a very simple reason of a range check. So when the prover is interpolating the user balances, we somehow need to constrain the prover to not put a negative balance into that polynomial. and also not to overflow the maximum possible value again to cause, for example, to cause the grand total to go lower than it actually is. So if we need a snark and we need to put that polynomial into a snark, then the question is, how do we do that? And how do we then produce the KZG commitment and the openings if we're putting the polynomial into a ZK snark? And here we are very lucky because Halo2 is actually doing all of that for us for free. We don't need to do any extra actions to accomplish these two properties. First of all, the advice columns in Halo2 are interpolated as polynomials inside the framework by the framework. And moreover, the values that you put into advice columns are interpolated as polynomials over the domain of the roots of unity. And as we remember from the previous session, this is crucial. This is essential for us to get the grand total as with the help of the constant coefficient of the polynomial. And the second nice property of Halo2 is that, at least with the PSE fork of Halo2, when we are generating the zero knowledge proof, the Halo2 is actually producing the KZG commitments to all the advice polynomials and putting those commitments into the proof. What we colloquially call a proof is called a proof transcript inside the Halo2. So here's the diagram that is illustrating all of the points. Maybe now is a good moment to stop for a moment and by looking at the diagram, just to make sure that we're all on the same page.
So Alex, do you manually put the coefficient in the table itself?
Yeah, here also a nice thing is that we actually can put the values themselves, not the coefficients, and the Halo2 does the interpolation for us. Well, this is not exactly true because in most of the cases, Halo2 is operating on the polynomials in value form, in evaluation form, without converting them to the coefficient form. But these details are like beyond the scope because we don't interfere with that process. For us, good news is that we can simply fill the table with the values and they will be interpolated into the polynomials.
I meant that the W to the power I for each user, do you enter those values into the...
No. They are a part of the setup of the circuit. So we don't need to do anything. It is just how Halo2 works. Many operations in cryptography are much easier to perform if your domain is the roots of unity. For example, FFT is much more performant if you're putting your values on the roots of unity, colloquially speaking. So that's why it has already been done in Halo2, and we're just taking advantage of this in Summa v2. I think there is a question in the chat. Can we print proof transcript in Halo2? I'm not aware of such a feature. I don't think it is possible, but there is definitely like in the prover code in Halo 2, there's definitely a place where you can figure out what is written to the transcript. There are quite a few things, quite a few commitments, and among them the commitments to the advice polynomials. Okay, I think if we don't have any more questions, we can proceed. So to recap what we have said, the under the hood in Halo 2, the advice cells are interpolated into the polynomials column by column. So each column gets a polynomial, and the interpolation is done over the domain of the roots of unity of the finite field, and the powers of roots of unity go from like 0 to the k-1. And that is exactly the same k that you might have seen in the circuit. And this is the size of the domain, size of the circuit. And the generated proof naturally contains the KZG commitments to the polynomials, but this is only for the PSE fork because the original Halo 2 is using the inner product argument as the commitment scheme. But we're using the PSE fork, so we don't need to do any extra actions to obtain the KZG commitments. So in this case, if we talk more specifically, what the prover should do is the prover should fill the advice columns with user balance values, and then simply generate the zero knowledge proof. By doing that, the prover effectively interpolates the balance values into the polynomials and also produces the KZG commitment points. The question now is, but how do we generate the opening proofs? If we are just filling the table with values, then we get the commitments, but we need to be able to generate the opening proofs from the same polynomials that were used to produce the commitments. And it looks somewhat like this, like we have the table with advice columns, and then each column is represented by a polynomial, and we need to, for any value that we need from the column, we need to generate an inclusion proof. So for this purpose, we had to do a small tweak to the Halo 2, and we are returning the polynomials from inside the Halo 2 while we're generating the proof. We can quickly take a look at the modification to the original Halo 2. The main difference is here around line 700, where we're returning the advice from the prover alongside with the proof transcript. So this was the only modification we had to make to Halo 2. And then when the prover has the advice polynomials at hand, the prover can generate the KZG openings for any points in those advice columns. So now let's take a look at our circuit structure. It is pretty straightforward. The balance polynomials are these columns here that are designated as currency 0, currency 1, and so on. And here it's time to remember that in Summa we're supporting multiple cryptocurrencies. That's why we need to have multiple balance columns in the polynomial. And as we said, we're using the ZK snark, like the full ZK snark here, because of the range check. That's why you can see that here for every currency balance, we need a corresponding instantiation of the range check chip. So here for currency 0, there will be a range check 0, for currency 1, range check 1, and so on and so on. And this range check chip is almost identical to the range check chip from the Summa v1. So you should be already familiar with that. If later you go and take a look at the code, you will not see many differences there. And the range check chips, they require a column of fixed values because they decompose the balance value into, in the case of Summa v2, we're decomposing the balance value in 4 2-byte words. So we're making all the balances to occupy 8 bytes at most. And then we check that the decomposition of the balance into 4 2-byte words belongs to, not the decomposition, but each of the decomposed values belongs to a table of all possible values that a 2-byte word can take, from 0 to 2 to the 16th. Here, maybe someone has already noticed something interesting, something that I haven't previously talked about, and this is the user ID column. And now we need to talk about something I briefly mentioned in the previous talk, is how do we make sure that that a malicious prover cannot reuse the same balance value and same inclusion proof for 2 users who have the same cryptocurrency balance. So let's take a look at that possible situation. So first of all, we assume that every user knows their index somehow. Maybe you can see it in the Exchange UI when you log into your user profile or in some other way. But anyways, as the verifier of the KZG commitment, you need to know that X value, because this is a part of the verification of the KZG commitment. So you will know it anyway. And then let's assume that there exists such a balance of the user J that is the same as the balance of the user I. For example, both of them hold 1 Ether on the exchange. So in this case, what a malicious prover can do is just to zero out one of the balances. Say for user J, set the balance to 0 in the polynomial, but then just provide the same proof as for the ith user, provided to the user J. So effectively, it means that the balance is included into the polynomial only once, and it understates the total liabilities by that value. So how can we use the user ID polynomial here to mitigate that? If we introduce such a user ID polynomial where for a user index, there is a value of user ID, in our case, it can be a hash of an email. So hash is nice because hash has a fixed length. Email may not have a fixed size, but hash, we can choose some kind of hash function that is convenient for us to use, but we don't need to hash it inside the circuit. If you think about it, you can notice that as a user, for you, it's enough to hash your email in this case, and you will know this value of, let's say, like off chain, offline. You can do it off proof. And then in this case, you will be checking your proofs against 2 different commitments to 2 different polynomials. You'll be checking proof for the ID polynomial and for the balance polynomial. And of course, you expect your ID to be the same for both of the polynomials, meaning that the X point for both polynomials should be the same. And the power of omega for both polynomials should be the same. In this case, the malicious a malicious prover couldn't provide you with commitment for a different user, for a balanced commitment for a different user, but with an ID commitment for yourself, because you would notice that the X value for these two commitments is different. Any questions? What do we do if the number of users exceeds the number of all possible rows? Well, that's a great question. The limit in Halo 2 is 2 to the 26th, and you can only fill 2 to the 26 minus 6 due to some peculiarities of how Halo 2 works. And we know, for example, that Binance is operating with a user base of 2 to the 28, not the user base, but the, let's say, the size of their proof of solvency solution. The maximum allowed size is 2 to the 28. So this is still higher than what Halo 2 allows you to have. And we will talk about it in the end. There is a very nice way how to deal with that, and basically have an unlimited number of users, as many as we want. But this will be in the end of the presentation. Now, you will have a chance to take a look at the full prover workflow in the code. It is contained in the integration test here. Now, I think we will not go through the code because this is too much details for today's presentation. But now we need to talk about a couple of things that are also very specific to Summa, to the Univariate grand total version of Summa, and that are slightly different from how you normally use Halo 2 in most cases. So you will notice in the circuit that we are using two kinds of advice columns, normal advice columns and so-called unblinded advice columns. So normally Halo 2 advice columns are blinded. And what it means is that if the column is filled with values by the prover, we need to still add some random values below to enhance the zero knowledge property of the KZG commitment. So for every proof, even if some of the assigned cells stay the same, by adding the random values below the assigned values in the column, the prover effectively randomizes the KZG commitment, so that even if some or all of the cells of the column happened to be to have the same value, by randomizing the unused cells below, the prover makes KZG commitments look completely different from each other, so that the zero knowledge property is strong. In our case, you can think about it. If we are filling, let's say our number of users is not always 2 to the power of something. It's probably some arbitrary number that is not a power of 2. So if Halo 2 tried to fill the rest of the rows by random values, in our case, it would interfere with the grand total that is encoded into the constant coefficient of the polynomial. And we cannot let this happen, because this will just defeat the purpose of this polynomial encoding approach. So we really need the polynomial to only contain the user balance values and be filled with zeros below that range. So in our case, we need to use the unblinded advice API from Halo 2. And in theory, this means that we are partially losing the zero knowledge property. But in practice, if you think about it, that to restore the polynomial from the KZG openings, you would need to collect as many of those openings as possible, and to restore the polynomial precisely, 100% precisely, you would need actually k+1 KZG openings if the degree of the polynomial is k. So in our case, the openings are the user inclusion proofs and also one proof for the constant coefficient of the polynomial. I would say that practically it's very difficult to imagine a situation where someone can bribe that many users, or that many users can collude to, for some reason, to try to estimate the balances of other users. And even if they do, I'm not sure that this estimation can be correct enough, can be precise enough. But this can be a very good question for this cohort of Y Academy for like assessing the zero knowledge soundness of Summa v2. So maybe we can stop here for questions. So again, the question in the chat: how do we know that the custodian is putting the correct balances inside the polynomials, and how can we verify that they are accurate? This applies equally to Summa v1 and any other existing proof of solvency, proof of reserve solution. The only one who can verify the correctness of your balances is you yourself. So there is no other way to verify it, and the reliability of this kind of proof of solvency solution relies on how many users will eventually verify their inclusion proofs. And this situation was the same with Summa v1. In the circuit, what we can ensure at most is that the custodian cannot put a negative balance or extremely large balance that will overflow after the, let's say, after the grand total calculation inside that polynomial math. So that is the only thing that we can make sure. The values of the balances we cannot be sure. Of course, there is no way to control the custodian here. The inclusion proof in V2 is the KZG opening proof for every user. This is also the question from the chat. So we have a KZG commitment, and we can produce KZG openings for any point of the polynomial. And of course here, since we have a polynomial of the user balances, then we are producing the openings of those user balances. What it means is that we are demonstrating to a user that their balance is indeed an evaluation of the polynomial at this value of x, which user expects because the value of x is their index, is tied directly tied to their index. For the user, it means that they were included into this polynomial. And since the same KZG commitment is also used to prove the grand total of this polynomial, then many users who verified their proofs can conclude that, yes, they were included into the polynomial, and also this makes them trust the prover in terms of the grand total. Okay, I think we can move on. And let's answer a very interesting question about can we put a number of users inside Summa v2 that is higher than the maximum size of the circuit? And the answer is yes. We can take advantage of the homomorphism of KZG commitment. If we remember how we actually do the KZG, we need a trusted setup, and then we kind of raise the trusted setup to the power of our polynomial coefficients. And then if we take a look at the math here for the KZG, we can notice that if we try to commit to a sum of the polynomials, the resulting commitment will look exactly like a sum of two separate commitments to each of those polynomials. So, which means that we can simply commit to two different polynomials, then we can add their commitments together, and it will be the same as if we first added two polynomials and then committed to the resulting sum of the polynomials. For us, it means that we can split our user base into as many chunks as we want, making sure that each of those chunks is small enough to fit into the maximum possible Halo 2 circuit, let's say 2 to the 26. And then we can interpolate all those polynomials and prove the first of all, we add the commitments together to imagine what resulting huge polynomial would be, and we can prove the grand total against that resulting commitment that is a sum of commitments of the chunks. And then we provide proofs of inclusion into individual chunks to every user. So here, users would be able to verify their inclusion into a chunk and then verify that the resulting commitment of all the chunks, the sum of all the commitments to all the chunks is indeed this value that is committed by the prover, by the custodian, and then verify the grand total opening against the resulting commitment. That is the sum of commitments of the chunks. And we have an example of this chunked approach in the repository. So you will also be able to take a look at how it works in practice, how you can add the KZG commitments together and then prove the grand total of the balances that went into the separate polynomials against a single commitment that is a result of summing the individual commitments. And that's it for today. This is the end of my talk. So let me answer your final questions. Okay, a question from the chat. Can the homomorphic property add malleability as an attack vector? Malleability in here I want to ask a question like malleability in terms of if the sum of commitments is malformed, or what exactly do you mean? I would say here, even, yeah, if I assume that this is what is meant by the question, then the answer would be, yeah, we can imagine a situation where a malicious prover is just maliciously forming the sum of polynomial commitments, which would mean that some of those commitments are incorrect. Then if there are any users who are willing to verify their inclusion into such commitments, probably they will encounter some problem, like probably their proofs would not check out. A valid commitment by a trusted party being transformed to another valid commitment by malicious party. I'm not sure that I understand this question because, well, if the commitment is valid, then what can you do to make it like I don't really understand this attack vector. Yeah, so all the KZG commitments stay public. Yeah. So this is an important point here. Let's go back. If we take a look at like the normal prover workflow, then prover needs to publicly provide the KZG commitments for everyone to observe. KZG commitments to individual here in this figure, these are KZG commitments to the separate balanced polynomials. Instead of a single KZG commitment per balanced polynomial per one cryptocurrency, you can imagine that there will be multiple KZG commitments. For example, if we have 10 chunks for like the entire user base, if we break down the whole user base into 10 chunks, then instead of one KZG commitment for a single balanced polynomial, we will have 10 KZG commitments, and the prover will publicly store them in the same way as if it was just one. And in our case, specifically, we're storing the commitments inside the smart contract in the same way as we were storing the Merkle tree root in version 1. And even more in Solidity, it's possible to do some basic elliptic curve operations so that we can potentially even store the commitments to the chunks and then produce the resulting sum of the commitments inside the smart contract. So this way we get the commitment to the total liabilities to the sum of all the chunks, and then we're verifying the grand total sum of the liabilities against the resulting commitment, against the sum of all individual commitments. But for the user inclusion, we're verifying the inclusion into a specific chunk that the user was assigned to, let's say. Some more questions from the chat. Why do we need chunking here? So actually, there can be one more reason besides the reason that was first asked in the chat. Like first it was asked about what if there are more users than Halo 2 can have rows? And we know that this is potentially possible because Halo 2 can handle only 2 to the 26th number of rows at most in a circuit. But for example, Binance has to do proof of solvency for 2 to the 28th number of users because they have a really big user base. So for as we can see, for a real exchange, 2 to the 26 maybe not enough. So we would have to split the user base into separate chunks. but we don't want to prove something separately about them. We want to still be able to connect them together, and that's why we can split our user base into multiple polynomials, but then we're connecting them by using the homomorphic property of the KZG. And the second reason that is even more practical, I would say, for smaller exchanges is just to parallelize the computation of the commitments. By splitting your user base into multiple chunks, you can easily run all your computations in parallel on multiple instances and produce the final result faster. Some more questions from the chat. Okay. How's the performance comparison of KZG version versus Merkle Sum 3 version? So here, to answer this question, first we need to talk about the difference between two approaches. Merkle Sum 3 has a huge advantage of not performing the range check during the commitment phase. As you remember, the commitment phase in Summa v1 is simply building Merkle tree outside of any zk snark and then committing to the resulting root. And the range check only happens inside the inclusion proof for every user, so that in that inclusion proof, you need to range check at most, like around, let's say, around as many values as there are levels in the Merkle sum tree. So let's say it's like a Merkle sum tree of 20 levels. So you have like 20 range checks, maybe multiplied by the number of currencies that you have in the tree. For Summa v2, situation is very different. Now, here you can see we are doing the range check right as we are putting the balances inside the polynomials. So we're doing the range check of the entire user base in the commitment phase, which makes the commitment phase much longer than for the Merkle sum tree approach, of course, because here we're also we're producing the zk snark proof during the commitment phase, similar to what Binance is doing. But the good news is that if we compare performance to Binance, for example, then our results are much, much better because we're using a simple polynomial instead of Merkle tree as what they're doing. In terms of user inclusion, the situation is also interesting. There is a trick that you can do for KZG to quickly calculate the user inclusion proofs. Not like user inclusion proofs, but of course, if we're talking about the general KZG, you can calculate all the openings of the polynomial at once using a special technique. This is a very nice approach for a smaller user basis, but for a larger user basis, it requires a lot of RAM, which sometimes is not feasible. But for the smaller user basis, it outperforms the Merkle sum tree approach. But we're still finalizing the benchmarks, so I haven't yet included them into today's session. So maybe we can include them in the following sessions or leave for you to study in your free time. Okay. Well, there is a question where there is a KZG IOP-based proof of solvency approach and a link to that approach. I will try to quickly skim through it, although I'm afraid that this I will not be able to answer this because this is someone else's someone else's proof of solvency solution. I think this is reminiscent of what Vitalik Buterin was suggesting in his article about proof of solvency. And as I remember, he was suggesting a KZG commitment because it's simpler than a Merkle tree, but the downside of that kind of KZG commitment that he was suggesting is that you would need separate, somehow like a separate way to calculate the grand total of the liabilities. And also the range check, I think, wasn't really covered in his article. But what I can say, like most definitely, is that by exploiting this interesting property of interpolating over the roots of unity domain and getting the grand total of the polynomial inside the constant coefficient, you are doing a huge performance boost compared to any other solution where you need to calculate the grand sum separately. Like where you need to actually perform the summation of balances, which we're not doing here in version 2. Okay, next question from the chat. How does the custodian provide KZG proof to a user? Do they do it privately? Yes, absolutely. This is crucial, and this is similar to what exchanges are doing today. If you need to request your proof of solvency, let's say from Binance, then you need to log into your user profile and navigate to a special page somewhere in your user profile, and you will be able to download your proof of inclusion there. So it should be similar to Summa, both V1 and V2. Next question from the chat. Wondering if one chunk per user may even be better performance-wise. Less bloated, hail to table, because you're only including columns for the assets a user has. Well, the problem then would be that if your polynomial has one value for one person, then you have a huge overhead, because if we take a look at, once again, at the full circuit structure, we have a range check table here that is filled with all possible values that a 2-byte word can take, from 0 to 2 to the 16th. So imagine that here you have only one row of user balances for each currency, but you need to range check that value against this fixed column that is filled with 2 to the 16th number of values. So it's definitely a huge overhead. And then also you will get, like, let's say if your user base is 2 to the 28, you will produce 2 to the 28 KZG commitments per one currency. That will definitely not be possible to commit to a smart contract, and also will be very problematic for users to verify, even if it was not a smart contract, but let's say if it was a script that you are supposed to run on your local machine, then you would have to download 2 to the 28 size of data just because of the number of the KZG commitments. So I think it's better to find an optimal number of chunks that will be convenient for, at least for the user to verify offline, maybe in a smart contract, but here we also did some checks and we realized that it heavily depends on the number of cryptocurrencies that you're verifying. Well, there are many questions in the chat. Yeah, would the commitments of a chunk and other chunks be provided publicly? I have already answered that. Yes. How can user, in this case, how can user ensure that everyone has the same total liability? So we are, let's imagine that we're dealing with the chunked version of Summa, where instead of one KZG commitment per cryptocurrency balance, we will have, like, let's say 10 KZG commitments per balance, because we break down the user base into 10 chunks. So according to the KZG homomorphism, what we need to do is to sum those individual KZG commitments to those 10 chunks to obtain the resulting KZG commitment that looks the same as if we actually first added all the polynomials together. And the grand total KZG opening proof is verified against this resulting commitment that is a sum of individual chunk commitments. This way, the user can be sure that, for example, if there are 100 users and they are more or less equally distributed across 10 chunks, so there are a few users for each chunk. At least one of them has verified their inclusion into chunks. That already tells us something about the chunks. And since all the chunks commitments are summed together to produce the resulting commitment, and the grand total proof is made against the resulting commitment, so that these users can trust the custodian in that the grand total is probably correct. And I think this was the last question from the chat.
I think there's one question that is missing answer, like from Ali, wondering if one chunk per user may even be better prover performance wise.
No. I have already answered this, and this is where we were looking at the range check proof and concluding that if you have only one row here, but you have 2 to the 16th row in the fixed column, then of course it's better that you should have a chunk that is at least the size of 2 to the 16th, so that you're at least filling nicely filling the table at least up to the 2 to the 16th number of rows that get filled eventually, inevitably, just because of the range check.
Thank you. I missed this one. Yeah, I think if there are no more questions, we can wrap up this session. Thank you, Alex. This was great. Yeah, thank you everyone for coming, and we're gonna post the recording later today, and see you everyone this Friday.
Thank you. Goodbye.
Thank you. Have a good day.